This mentoring session focuses on the Alexander cell not just as a concept, but as a practical and powerful tool for understanding and controlling corrosion in real conditions. Most traditional corrosion measurement techniques rely on electrical potential readings. However, these methods do not actually measure corrosion itself. They only measure the electrical balance. This can often lead to misunderstanding, especially when readings fluctuate. The Alexander cell is different because it measures actual corrosion current. This current is the direct result of metal dissolving into the electrolyte, which means it represents real corrosion activity. According to Faraday's law, the amount of metal loss is directly related to the current flowing. Therefore, if current is flowing, corrosion is occurring. If the current stops, corrosion has stopped. If the current reverses, it indicates that the protection is not only present, but actively overcoming the corrosion process. The construction of the Alexander cell is simple, but precise. It is made using steel similar to the structure being tested. It consists of a bright polished anode on the top, a passive cathode and two base electrodes that make contact with the ground. All components are embedded in an insulated epoxy body, ensuring that each electrode is electrically separated. It is essential that the anode is polished before each use to allow a strong electrochemical reaction, while the cathode remains unpolished to maintain its passive condition. In operation, a sample of soil or backfill is placed between the top anodes. This creates a corrosion cell where the polished anode reacts with the electrolyte and generates an electromotive force. This EMF drives a current through the measuring circuit. The base electrodes connect the system to the ground, completing the circuit and allowing currents to flow to and from mass Earth. This is a key advantage of the Alexander cell. It allows measurement of current entering and leaving the ground, something that conventional instruments cannot achieve. When the Alexander cell is connected to a pipeline, the electrical potentials of all its components become equal to that of the pipeline. At this point, cathodic protection, current, and other electrical influences in the ground can affect the corrosion reaction within the cell. If the cathodic protection is strong enough, it lowers the potential of the system below its corrosion level. As a result, the current in the Alexander cell reverses direction and the corrosion reaction stops. This provides direct and immediate proof that corrosion has been controlled. The operation of the Alexander cell is fully supported by fundamental scientific principles. This includes Faraday's law, which relate current to the metal loss, thermodynamic principles that govern energy balance, and electrochemical relationships that define the interaction between metal and the electrolyte. While these principles are often expressed in theoretical equations, the Alexander cell demonstrates them physically and visibly in real-world conditions. Another important advantage of the Alexander cell is that it avoids common measurement errors found in traditional methods. Many techniques are affected by voltage drops in the soil or external electrical interference. The Alexander cell overcomes this by measuring directly at the anodic interface in a closed circuit condition, ensuring that the readings reflect true corrosion activity. A field experience has shown the effectiveness of this method. In practical tests, measurable corrosion current was observed before connecting to the pipeline. After connection, the current either stopped or reversed, confirming that the cathodic protection system was sufficient to control corrosion at that location. Further developments of the Alexander cell have improved its performance and flexibility. These include modified base electrodes designed to allow current to flow from different directions, detectable anodes for consistent preparation, and designs suitable for both laboratory and field use. The key message is clear. Corrosion is not simply about electrical potential. It is about current flow, charge movement, and real electrochemical reactions. If no current flows from the metal into the environment, no corrosion can occur. The Alexander cell makes this visible and measurable. In conclusion, the Alexander cell is more than just a measuring device. It is a complete method for understanding corrosion, verifying protection systems, and applying scientific principles in practical situations. It provides immediate, reliable results and gives engineers and coordinators a much deeper level of insight into the true behaviour of corrosion. Thank you for your attention, and it is important that this knowledge continues to be shared, developed and applied in practice.